Good morning, everyone, or those who survived the night. That apparently, from the WhatsApp chat, was quite wild. Um, so let's start from where we stopped yesterday. So just to recap briefly, yesterday I tried to guide you a little bit through a couple of simple models that describe some phenomenology of active matter and collective behavior of self-propelled units. We saw that once we kind of inject some form of energy that we still need to actually quantify, but we are in the position, once some kinetic parameters are tuned, to create phases of matter that are not there at equilibrium. And so I also quickly, at the end of the presentation, I also quickly mentioned this, we can try, or physicists would like to try, this measure of irreversibility as a quantitative measure of the free energy that is dissipated by the system, and we will see by tomorrow that how this thing works. And I will, maybe it was a bit fast, but I will come back to that tomorrow. Before that, today, what I want to do is, okay, we have this effective description on a very coarse scale that captures some kind of dynamics that we see in experiments. And what we want to do is to assess whether this kind of description is also good to understand how much energy, the thermodynamic cost of these transitions, we can obtain from these descriptions. What we actually have to do is to go back and see what we are really talking about. So what are these microscopic units? And I will stay on a microscopic level here, where thermal fluctuations are relevant. What are these microscopic units? How the motion is actuated? How forces are converted into motion? And so how this free energy transduction works. So what I'm going to discuss in some details, but hopefully not too much, but just to give you a broad idea, is let's try to see what are these self-propelled units that, for example, you can take as the building block, so the single units that enter this active Brownian particle model, for example, okay? So this model is, under some conditions that I will describe later, is believed to be a good description for example, for this kind of objects. So on the left-hand side here, these are what are called essentially these microswimmers. So these are biological microswimmers in the sense that you see a variety of microorganisms, or from bacteria to also to single unicellular organisms like the sperm cells. And what they do is that you see a scale here, this is 10 microns, and so you go from a few microns to a few tens of microns. And so essentially you are on a scale where you are at the border of where Brownian motion is relevant, but for sure it's on a regime, I will discuss that later, where inertia is certainly has very little relevance, as it was mentioned by Anupam last week. And I will take the opportunity to discuss maybe a little bit better things that Anupam said about the hydrodynamics of these swimmers, maybe to clarify and to put something more in the context. So these are swimmers in the sense that they are able to transduce some chemical energy into directed motion, and they do that because they perform some periodic deformation of their body. So they can have some cilia, flagella, that they move periodically, so they can beat them, and such a way that at the end of these revolutions of these appendices, they essentially displace in the aqueous environment, in the fluid in which they are, okay? And so on a very coarse scale, you can imagine that you can describe them as giving them a direction, which is the typical direction of their motion, and some kind of excluded volume on a very coarse and rough scale. So this is one class of system that I will go to explain a little bit better how they can actually move. And another system which is a man-made with synthetic system is this called Janus particles. So these are really colloidal particles. You see maybe a scale here. It's 800 nanometers here on Guy. And this is a bunch of active particles. So these are like usually polystyrene beads that this is actually how they are created. So they put them on a plate. And then by deposition, you just cover half of them with some materials that make them different. So they give them different physical chemical properties to the two halves. This in particular was probably coating them with some metal, I would say gold. And what's the interest in doing that? Well, the point is that now you can exploit these two different halves to produce gradients. We will see what kind of gradients, and these gradients across the surface can essentially move the particle along the symmetry axis. Okay. Before going more into the details, let me show. Basically, these are the guys that are moving. And how the motion is actuated, well, at the more microscopic level, is that for the biological swimmers, they utilize a bunch of different methods to move these protrusions, these flagella, these cilia, and this is their motion. The motion of these flagella cilia is actuated by molecular motors. Okay, these are. I just put two kind of examples here. This is like a bacterium flagellum that is like, this is the membrane of the of the bacterium, and you have this rotor protein that is just well, depending what kind of microorganism you're talking about, can be by ATP synthesis or by a proton gradient. You are transducing this kind of chemical energy into mechanical work, which is just a torque. Okay, that is moving this flagellum, which is anchored on the membrane, and so this will be the rest that is then performing this periodic motion in the fluid. Okay, and on the other hand, here is like it's a eukaryotic flagella, like for example, flagellum of a sperm cell, and this would be like the cross section. If I take the flagellum, I just cut it through, and I have these kind of structures. And these bundles of microtubules, they are essentially bent and twisted by molecular motors, by Dunning molecular motors. Okay, so they use ATP in order to create forces, and you create these periodic motions. This, you can imagine, is quite complex. There's a lot of the chemistry and biochemistry that we heard before, because it's sustained by metabolism of these organisms. So I would say that it's a good starting point as a kind of proxy to understand, to simplify a lot the problem, to think about these other units, these synthetic units, these Janus particles, that are moving in a very simpler way, in the sense that the energy that we provide to them, and then the mechanism we turn this external energy source into motion, it's far easier to understand. So this is a zoom of the surface of this particle. So imagine that we zoom in such that we just flatten the surface. So this is the particle, and on this particle, we because of the two different halves, we create a gradient. So for example, it could be that we shine laser light on these particles, like the one that I showed you before. The metal part absorbs more light than the polystyrene part. This, then it heats up, heat is released in the environment, and then we create a temperature gradient across the surface. Okay, and that would be the gradient that is created when we zoom in and we look at the surface. But this can also be that we have coated this half with a catalyst, such that when we put this particle in a solution with a certain substrate, this catalyzes some certain chemical reaction, and so this creates a gradient of some chemical species in the surrounding. So whatever kind of gradient you have, this can be like can be non-charged species, ionic species, whatever. The resulting mechanism is what is called phoresis. So phoresis is whenever you have a certain surface, you have a gradient across it. And because of the imbalance in stresses essentially on the solute and the solvent, the result of that gradient is that you create a flow field. So the solvent is set into motion on the particle surface, and this is because of the imbalance of the interaction between the particle and the solid molecules, okay? So the result is that you create what is shown here. So this would be like a slip velocity, okay? Once we zoom out and we look at the particle from distance. So this is a tiny boundary layer. On this boundary layer, because of the imbalances, I repeat, created by this gradient between the interactions, on the interaction between particle and solvent, we have this slip velocity. So then altogether, since we are not applying any external force, there's just an imbalance between the forces between the particle and the tiny boundary layer. The two things, they have to be force-free. So essentially, the particle moves in order to kind of cancel this slip velocity, such that particle plus the tiny boundary layer, they are force-free. Okay, this is essentially, in a nutshell, the idea of phoresis. Self-phoresis is because the gradient moves with the particle itself. So it's not that we, as I told you yesterday at the beginning of my lecture, we are not breaking the symmetry from the outside. We are not putting gradients, okay, on the boundaries of our system, but this is really created by the particle. It's co-moving with the particle itself. So as the particle moves and rotates, for example, because of rotation, translation, and Brownian motion, this gradient follows the particle. Okay, so this is our essentially these two mechanisms. And so let me just, I want to spend a couple of some minutes more to discuss about microswimmers and phoretic swimmers, because this gives you an idea of how, well, as I told you, because we try to maybe clarify some things that were said last week, and gives you an idea of how these things move, where the energy comes in at the microscopic scale. Okay, so let's just let's go back for a second to this, what I call the swimmer. Okay, so this is a swimmer, as I told you, is an object that performs periodic motion or periodic movements of its body, and I will tell you in a moment what I mean with that. So, and these guys are microscopic. So we said that their typical length scale, let's say there's a length scale R that is gonna be around 1 to 10 microns, okay? And they move in an aqueous environment. So they move in water, let's say, or in something that is, let's say, more likely something viscoelastic, but let's talk about simple fluid like water. And so the idea, you can imagine the shape of this particle. When you look at them on a cursor level, you can imagine that they have a certain shape, and given a certain reference frame, there's gonna be a vector, let me call it Rs of t, that describes the position of each point of the surface, okay? So this is a vector that tells us where the surface of the particles is at a certain time. And this guy is gonna move, is gonna change in time, okay? And this is what I call the surface, the velocity, okay? So this can be because you imagine that you have this cilia on top that they are moving, or because you have a, you have your bacterium with a flagellum that is changing, okay, is rotating, okay? There will be some certain velocity of this overall surface, and the fact that is a swimmer means that this is a periodic function of time, okay? With a certain TP, which is the period of the body motion, okay? And so this is in water, and so as an object that moves in water, well, we're not going to describe all the molecules of the fluid and how they interact with the object, but we're going to take a sort of coarse hydrodynamic description. And so you know that conservation of momentum at the hydrodynamic level is described by the Navier-Stokes equation. So this tells me that the density of the fluid times the time variation of the flow field, okay? The flow field V is gonna be the velocity of the fluid around this particle, okay? Changes in time because there is an explicit time dependence, because the particle is moving, so it's agitating in a time dependent way the fluid around, but also because, of course, if I move along one fluid line, essentially the velocity is changing, okay? So there's an advective derivative. And all that is due to the forces, which are the gradient of the pressure and pressure gradient, and the viscous forces. Eta is the viscosity of the fluid. Okay? This tells us how momentum is conserved. Essentially here momentum is inputted by the particle, and we will see in a moment how, and then it's transferred to the solvent. So this is a general description of a fluid in motion. Of course, there will be the density, the fluid density, so conservation of mass conservation is expressed by the fact that there's a continuity equation for the density, okay? And that's it, almost. Well, we just have to say that at the boundary between the fluid and the particle, well, the fluid has to move with the same speed of the particle, right? Because there is viscosity, the fluid sticks on the surface of the swimmer, and so if the swimmer is in motion, as a surface in motion with a certain velocity, well, the velocity of the fluid must be the same. So the velocity of the fluid on the surface of the particle at any time must be equal to the velocity of the body, okay, which I called u, plus the velocity of the center of mass of this object, okay? So if I put myself in the reference frame of the swimmer, of course, the fluid will stick on it, but if I stay on the reference frame of the laboratory where I see this particle moving at a certain speed v0, okay, I'm not using v0 because it's the same v0 that we used before, well, the fluid velocity at the surface will be the sum of the two. So this slip, okay, this kind of slip velocity due to the body motion plus the velocity of the center of mass, okay? But then there is this point here. And the point is that we are living these guys are living on very small length scale, okay? It's in around micron. So it turns out that if you look at these equations, not all terms have the same relevance, and their relevance changes with the scale, right? So what you can do, usually you do a kind of analysis of a dimensional analysis of this equation, and you look at you just compare the two main players here. One player is just advection, so this is how momentum is advected by the flow. So this is this part, which is also the nonlinear part, okay, of the equation. And you compare it, like the modulus, the absolute value, you compare it with the viscosity, so the viscous forces that are acting on the other side, okay? You look at these two guys, and if you do, so this is viscosity, and this is the advection, okay? So there's also a rho missing, otherwise they are not the same guys. So it turns out that if you do a dimensional analysis, this guy goes like the typical density of the fluid, okay? The typical velocity in our system, where the typical scale is the center of mass velocity, so it's V naught. And then we have the typical scale, which is the radius of the particle, or I called R the typical dimension, so it's not, doesn't need to be a sphere, this guy, okay? And then there is the viscosity, okay? This is just a simple analysis where I say typical gradient of the order V naught divided by R, and Laplacian of velocity is V naught divided by R square. Okay, it's a simple dimensional analysis that I construct with the typical dimension of my system that I have. Okay, it's a global analysis, of course. And this guy is what is called the Reynolds number. Reynolds number, right? So this guy is telling you that if this combination, which is a dimensional combination of quantities, is very large, it's telling you that this part of the equation is dominant, okay? This is the nonlinear part due to advection, and if you put a bit of numbers, you see that this is the quantity that is big when we look at motion on a macroscopic scale, right? This is large, this is of the order of 10 to the 5, 10 to the 6 or more for macroscopic objects, like meter, something of the order of the meter, moving in whatever air or water, with a velocity of meter per second or so. Well, this equation is telling you that you can essentially neglect viscosity almost everywhere, and you get this equation that is very nonlinear. And of course, when you have a nonlinear thing, you will have something that becomes chaotic and turbulence, and that is what we have for macroscopic fluids. But this is not where we are here. For microscopic objects, it's the other way around. If you put a bit of numbers for these objects that typically move with a speed which is around a micron or 10 micron per micrometers per second, well, you see that the Reynolds in water, okay, so you take the viscosity of water, 10 to the minus 3 Pascal per second, density, 10 to the 3 kilograms per square meter, you get that the Reynolds number for this microscopic swimmer is around 10 to the minus 5, 10 to the minus 6, something like that. Let's say 10 to the minus 5. So it's extremely tiny. So it means that it's the other way around. This term is completely negligible. We can cross it out. And what dominates is just viscosity. So it's a completely different word than what we are used to, right? It's a completely different word because all this part that is related to inertia, just let me put this aside for a moment, all this part that is related to inertia is negligible. So at the moment where I stop to push, imagine that this swimmer is pushing, so with this periodic deformation is pushing on the fluid. When you stop to push, you immediately stop. There's no inertia going on here. So it's completely different, for example, from how we swim in water, when we have these power strokes, and then we rely on the fact that there is inertia that pushes us in the forward direction. Okay, so what we end up with is not the full. I have to not cross. Don't have to cross this. So sorry. We end up essentially with the Stokes equation. Stokes equation, which is what remains there, okay? I keep this guy for a moment, the explicit time derivative, and I crossed out the nonlinear part. Okay? Okay, so this is the time-dependent Stokes equation, and this time dependency in principle should be there because this guy is performing a time-dependent motion, so it's a non-autonomous problem, right? But actually, you can do a similar analysis also here. So you can look at what's the typical magnitude of this term if you compare it back with the viscosity term, right? So what you can look at, what the important quantity that enters here, is essentially the frequency of this motion, okay? The frequency of this motion determines how big, together with the density of the fluid where we are in and the typical velocity V naught, determines the dimension of this object and the magnitude with respect to the other. Well, it turns out that for the typical frequencies that are in here, well, we can see that frequency, so the inverse of this period of the body motion, this T is way larger than rho r square eta, okay? So this is just an analysis that these numbers comes from just order of magnitude analysis of this term and of this term, okay? And this guy here is the typical relaxation time of the fluid, okay? It's the relaxation time of the fluid, okay? It tells us what's the time needed by the fluid to diffuse, because the Stokes equation is essentially a diffusion equation, okay? Diffuse on an area that is given by the particle size squared, okay? And this period is way larger than that. So essentially, it means that the fluid motion is always at steady state with respect to the motion, periodic motion of the particle. So this means that we can cross out this term, and we can go to the time-independent Stokes equation, which is just a balance equation between pressure forces and viscous forces, okay? So this is the good equation that describes the motion of a microswimmer together with, so this is still, you have to solve it at any time. At any time you will have a different boundary condition, right? Because this is time dependent, but it's still like a quasi-static. It's a sort of quasi-static motion of the particle once we compare it with the time scale of the fluid. Hydrodynamics is instantaneously equilibrated, essentially. Yeah. 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 If you put yourself on the center of mass of the object, and you look at the speed of that particular point of the surface. So it depends also on R of S. Yeah. Yes. No. It's way more short times. So tumbling. Okay. So I wanted to discuss this maybe later, but this is like this bacterium is rotating thanks to this motor at the basis here is rotating the flagellum. Okay, and this is on a certain time scale. Okay, and then so it's moving essentially straight apart from small fluctuation, and then at some point it can reverse the direction of the flagellum, for example, so it can tumble that way. So tumbling is on a larger time scale. This is really the displacement of the body surface in order to generate motion. This has to be is periodic. Okay. Okay. And okay. So what you want to get out of all that is this number, right? This number, I've just used an order of magnitude here from observation, but out of this set of equations, you want to calculate this number. At that point, is an unknown, okay? You know all the rest, you know the dynamical equations, the boundary conditions, you know the value of density and viscosity, etc., but you want to calculate that. So how you calculate that? Well, you impose that essentially, well, this is swimming, so it means that it's moving by itself. There's no external forces that drive this particle, right? So this body has to be force-free. So the particle, with its boundary, with this layer, which is set in motion with that speed, has to be force-free. So what does it mean? It means that we just have to calculate the force. What is the force on the particle? Well, the guy that I just deleted, no, it's here. This guy here, you can write as the divergence of a tensor, okay? And this is the so-called stress tensor that tells you what's the force in what direction for a unit of area with oriented in another direction, okay? So this guy has these two indexes. It has a diagonal part that is composed by minus pressure, and it has an off-diagonal part that is composed of this strain rate, okay? It's given by the viscosity and the gradient of velocity, okay? So the force then is you just obtain the force integrating on the surface of the particle, the stress tensor times the normal to the particle, okay? So this guy, in any point, I will have a normal vector, unit vector pointing outside, okay? If I take the product, the scalar product between the stress tensor and this vector, I get the local force on the particle, okay? And this, I want it to be zero, okay? There are no external forces acting on this particle. It's not that there's an external field that is dragging the particle, okay? Yeah. TP, I would have liked, I thought I wrote it down, but now I don't remember anymore. The right-hand side of this quantity here, this is a very small number. Yeah, this is the typical relaxation time of water on this time scale. Is around is fraction of milliseconds. Sorry. Yeah. But this is a tiny number, okay? It's the order of probably tens of microseconds. Yeah. I mean, this is the thing. This is the guy that when you do essentially Brownian motion, you are always assumed to be infinite. Okay, when you write your Langevin equation, and you say that your v dot is minus gamma v plus whatever plus noise, in order to assume that the friction is just an instantaneous function of the velocity and does not depend on the whole history of the hydrodynamics, well, because you are setting this to infinity, right? So it's not some weird assumption that we are making. I can give you the I can give you the numbers later. I don't have the numbers here. I thought I had written them in my notes, and I don't have in my mind. Yeah. So that the okay, 1,000 revolutions. So that TP is a milliseconds, and the other one is tens of microseconds probably, or 100. Okay. If someone has their exact numbers now, you can tell. Okay. So from this equation, well, imposing this condition, we can get that guy. Okay, we get this unknown. Okay, that's good. And that's essentially how it works. And there is a caveat here, and it's related to the fact that I told you that swimming at this low Reynolds number is very different from swimming at high Reynolds number. Well, everything boils down to the fact that this fluid equation is essentially completely invariant under time reversal, in the sense that if I swap at the same time the velocity and the pressure gradients, okay, this velocity, this equation doesn't change in form, right? So this, as a consequence, turns into a statement that regards the motion of the swimmer. So if the swimmer is moving his body in a so-called reciprocal way, is not going to move on average. I have a question, then I clarify. Yeah. Because you solve this equation plus that. Well, this usually you simplify. So you say that there's an incompressible fluid, so you set this to 1, okay? So you have this equation and that equation. With that, you can solve for P and for V, okay? This you solve given that you have at any time with this U and this V naught, okay? So this is a linear equation, so the field V will be linearly dependent on V naught, okay? Then you calculate the stress tensor, which is a function of P and V, so it's a linear function of V naught. You plug it in here, so this inside here there's gonna be something that is linearly dependent on V naught, plus constants and so on, okay? And this is an equation that you impose in order to get V naught. There is the boundary condition. Boundary condition. Okay? You have to adapt at any time to this boundary condition has to be fulfilled at any time. Okay? So when you solve it, these fields, they will depend linearly, because the equation is linear, on this boundary condition. So there will be, this V will be some kind of function of V naught. So when you go there will be a V naught somewhere. Okay? So when you add another equation, you can solve for V naught. That's the idea. Then here I'm not considering like rotation and so on, because this guy can also rotate, so let's not consider that there's a torque, and then we also need to set the torque to 0, okay? Yeah. neglecting the acceleration of the swimmer. Yes. Yeah. Yes, if maybe if you want to frame in this way, that's probably a good way. Yeah. Okay. What? Now, it's the point is that there's no acceleration because there is instantaneous adaptation to the boundary condition, to the boundary condition, in order to have no force. Okay. Yeah, it was interrupted by so so if there is a reciprocal motion, and I'm going to tell you what reciprocal means, then V naught is 0. So reciprocal is that the series of movements that the surface does is the same under time reversal. Okay, so imagine that this swimmer is doing some kind of, is displacing his motion in a certain fashion, is doing a series, as a section of displacements. If you look at this series backward in time, and it's the same, it's a reciprocal motion. Note that I'm not talking about the speed of this motion. So imagine that, well, this goes under the name of scallop theorem, because if you take the scallop would not be able to swim at low Reynolds number. So it's the scallop is doing essentially this, and this the motion here is just opening and closing, right? So reciprocal this is exactly a reciprocal motion. So if you look at this opening and closing, if you look at it in a time reverse way, it's still closing and opening. It's the same. And look, I'm not the velocity, so the rate of this motion doesn't matter. This you can prove it. It's very easy. Even if you open very slowly and you close very fast, this doesn't matter. You can reparameterize time because there's no explicit time in this equation, and what matters just the sequence of movements. So if this sequence of movements, independently of the length in time, is the same, you're not going to move. Okay? What? Yeah, sorry. It's I was going back to. This is the V naught. Is the particle? Is the center of mass velocity. So there's no center of mass velocity on average. So that is this is essentially to be is 0 on average, what the average is on the period. Okay, that's the important thing. Yes. Is there a geometric Yeah. Yes. It's the same here. If you can show that you need, thanks for the comments, and indeed you need at least 2 degrees of freedom to cook up on a no reciprocal motion. So just with the degrees of freedom, you can do that. You have scallop. This I think so. I believe that I've seen this kind of results where the area inside determines, but I'm not sure. I'm no expert of that, but it could be very true that yeah. With one angle, with one angle and a periodic conditions. I don't. you exactly. It's yeah. I mean, it's not. I mean, it's not really a single. I mean, you have to sneak in something like a periodic boundary condition or something. Yes, but with the flagellum you have the chirality. So essentially, if you look at one point, it's if you look at one at a certain. I mean, if you look at one angle, then these, you know, if you have your flagellum and you cut it with a plane, and then you look at the certain angle, well, this angle is not staying at the same distance, right? From the attachment point. So actually, you have to consider also the distance, so that there's a length also. So there are two variables. At least this is a simple way to parameterize. Maybe that can have another one with a. No, that doesn't. No, doesn't. That is not. This is completely time. This is reciprocal. Yeah. It's important. The important thing is that this. The rod is not chiral. Yeah, but you were. I thought you were talking about just the road. I know, because you said road. I was just referring to the road. With the road, doesn't. With the chiral, yeah. Yeah. Yes, but I mean, I don't actually see how you get one. I mean, to describe the chirality, but to describe the chirality, you need another parameter. Just one. But with the helix, I mean, I told you, if I just parameterize that, I look at a certain distance. Yeah, but if I look at the distance, at a certain distance, I mean, I look at a point of the helix, and I look at the angle. This point is not staying at the same distance from the attachment point. Is if you open a pen and you take the spring, and you know, you as a corkscrew, you use the spring on the paper. If you move the angle, the spring is not staying at the same point. If you want to make it the same length, is elongating or contracting. But it doesn't. I mean, we can discuss later. Okay. Okay. Good. So. Okay. So. So this is just for how the motion is actuated, and of course, if I look at this guy, let me delete all these things. So this is how the motion is actuated for a swimmer that does some reciprocal displacement of the movements of the surface. Well, I took so much time for that because essentially you can reuse everything for the phoretic particle. For the phoretic particle, well, so the idea is that, again, you have this particle. In the simplest case, you just have two different alts, and you are either catalyzing some reaction or you are absorbing more heat or something like that. At the end of the day, what you are doing is that you are creating a gradient of some field, and what is important is that is the parallel part of that gradient. So the part that is tangent to the surface. Yeah. The previous calculation was I set up everything to show to make you to understand that you can calculate can obtain the velocity of the object after a period, imposing the fact that it's a force-free object. Okay. From that fact, I didn't show that, but from the fact that you have this Stokes equation which is independent of time, and invariant under time reversal, the result is that you can have motion only if you have this reciprocal variation of the surface. Okay, so I just wanted now to show you that this is essentially the very same thing, the very same theory that you apply, that you get that you apply to have the motion of a Ferretti particle. Because essentially with the Ferretti particle, what you have is, because of this gradient on the surface, you create some stresses, some unbalanced stresses on the surface of the particle. And these, at the end, they set fluid in motion on a certain boundary layer of a certain thickness, let's say, of order L. Okay, so there is a boundary layer, and in this boundary layer L, which is typically much smaller than the size of the object, because of these gradients, you set the fluid into motion. So if you look, this L of course is exaggerated, it must be much smaller. So if you look at this object from far, is very similar to what we saw before for the swimmer, because there is a slip velocity, okay? So there is a boundary condition such that the fluid velocity on the surface has to be equal to the center of mass velocity of the object plus this leap velocity, which is the terminal velocity here at the upper hand of this boundary layer. Okay, so formally the problem is the very same. There is a slip velocity. Now it's not time dependent, it's just a constant. Okay, is a constant slip velocity, and you need to have this condition. Okay, this slip velocity is going to be something which is proportional to the tangential gradient that you impose. Okay, and at the end of the day, this guy is going to move in order to stay force-free, in the sense that the body plus the boundary layer that now has been shrunk down to essentially the surface of the particle has to be force-free. Force-free. Okay. So the idea is that if you look at the particle on a scale where you can resolve the interaction force between the surface and the solvent molecules and the solute, if there is also gradient of chemical species. Well, there are these forces that went unbalanced because of the gradient. This creates a small, on a tiny layer on the particle surface, a slip. Then if you zoom out, this slip is so small, this boundary layer is so small, that you look now at a single object, okay, with directly this slip velocity on its surface, okay? And the 2 has to be force-free, because the force that the particle exerts on the boundary layer is equal and opposite to the force that the boundary layer exerts on the particle, such that at the end they move with a certain velocity. Okay, that's the kind of idea. And many times, like in applications, people like to have particles like with diffusiophoresis. Okay, well, where you can use, for example, hydrogen peroxide, which is catalyzed at a coated surface, which is coated with platinum, and this, let me get it right, H2O plus H2, right? Plus O. Okay, with the catalyzed by platinum. Okay, so you have this reaction that is catalyzed, and then you have this gradient that is created on the surface. So this gradient here is going to be like this phi here is just now concentration of hydrogen peroxide. Okay, and this is what is very much realized in self-metric experiments. This is one instantiation, one example. Okay, yes. The slip velocity is tangential to the surface. It cannot go in because the particle is, I mean, it's a solid particle, it's not a porous one, so there cannot be inflow or outflow. Okay. V0 is in 3D. By symmetry, it's gonna be just along the symmetry axis. Okay, because there will be, here there's a rotation symmetry. This object has the symmetry axis. Okay, so at the end of the day, it's gonna be 3D. Okay. Okay, so so actually here to achieve the motion here, you see that essentially we have described almost everything. There's nothing but a gradient. You can go into the details, and I will do that tomorrow a bit more, of the force imbalance, but at the end we have all the mechanisms that generate the motion. So the example of the Ferretti particle is a very good example if you want to go and build sort of go through the scales and try to understand, well, how much free energy do I use to from that reaction I can convert into motion, and then it results in a collective motion of a multitude of these particles, and how much of that, so if I can quantify that at this level, I will do that tomorrow, and then you can go up and build consistent dynamical equations that are thermodynamic consistent, I mean, through the scale, where I have a collection of Ferretti particles, and I can see from the hydrodynamics at that level of this collection of what they're going to be like active Brownian particles, that now I can describe their microscopic way of motion, how much of the energy I can get from this coarse grain level. Okay, for the streamer, of course, what we provided was just a dynamical description, because we are assuming that there's this slip velocity. Here the slip velocity, instead we can see how it arises. It's just an imbalance of force, interaction of force between solid and particle. There is due to the collective, the motion of the surface. So if we want to try to understand the energetics there, we have to go even deeper at the level of the molecular motors that are working. Maybe collective is a collective motion of many molecular coordinating molecular motors that generate the motion of the flagella or whatever that then is described effectively as a surface displacement of the body. Okay, so in the rest, yeah. No, it's not tangential. I'm just saying that what matters is the tangential part. The rest doesn't matter. It doesn't contribute to, it doesn't create a slip velocity, and so it doesn't contribute. In the theoretic theory, it doesn't do anything. Okay. There's tomorrow I'm going to tell about this. So tomorrow, what I'm going to do is I will start from a model where I'm essentially describing surface substrate to product chemical reaction catalyzed on half of the particle. Okay, there will be different interaction energy. So the substrate has an interaction energy with the particle. The product has a different interaction energy with the particle. Okay, at the infinity there will be chemostats that keep the concentration fixed. Okay, and then from there I will sketch a little bit how you get to this guy. And then from there, once you have the velocity, you also have the thermodynamics good there. And then you can go to you can construct the model of the active Brownian particle model where you know now the velocity and the mechanism for that. And then you can do another step and go to many particles that are interacting, okay? And then you can look at the hydrodynamics and see how it compares down with this molecular kind of description, okay? This I'm gonna do tomorrow. Yes? Here everything is done with the constant density. Yeah. Of the solvent, of the fluid, of the solvent. Yeah. If it's not homogeneous, you can have that part gradient part. Yeah. That's. Yeah. Yeah. It won't move because there will be no gradients, no tangential part of the gradient. There can be a radial gradient, but no. If the shape is all over not symmetric, I would say, I mean, no, because I still don't get a tangential gradient, right? You don't get at the surface a tangential gradient, I would say. No. Okay, so before doing tomorrow what I told you, let's try to look a little bit more into the harder problem, which is the one of the swimmer, not the complete problem, but of course, let's try to understand. We take a step back to the more microscopic level of a molecular motor, to see if even at least at the level of a molecular motor we can say something about how to understand how the free energy is converted into mechanical forces. So I have to go a bit faster than expected, but just to give you an idea. Okay, so this is one example of a model, a very simple model of like a motor protein. So this is kind of the schematics. So this is a Markov-John process for a molecular motor. So it goes like that. So we imagine that we are talking about like motors, like I don't know, myosin, stuff that is moving along a track, like a microtubule, something like that. Okay, and so this is gonna be like a space coordinate. So you are advancing or going back on a certain track, and your protein, your motor protein, has a set of internal states, which is like different conformations that the motor can be in when it sits on a particular place of the track. Okay, so this is like the cartoon where you have a teach point in space. You can go into these different internal conformational states. Okay. And I'm going to tell you how the dynamics should be. Then, of course, you can also move in space, okay? And so you can move from one state to a close by state along this track, okay, which is separated typically, this order of magnitude is a few nanometers. And so you can jump from an internal state at some point to an internal state of a nearby point along the track, okay? Which is like a filament, so it's periodic. And so the periodicity is here replicated by the fact that you have these internal states that are the same, just located at different point along the filament, okay? So there is, if you want, the conformational state, and there is the spatial state here. So you also imagine now that when you move in space, well, this motor is, of course, carrying a load, so it's feeling a force, and this force is the one that is entering the dynamics or the rates that I'm going to write down in a moment, where you move from one point to the other along the filament. So when you move on this filament, well, there will be a force that you have to overcome. How to overcome it is because you are, for example, hydrolyzing ATP in order to favor this transition with respect to the opposite one. Okay, this is the kind of it's a kind of very simplified model. Okay, so here I cannot write. There I cannot write, so let's just take this out. Okay, so remember now that I have written down these Kij that are transition rates for between internal states. And with internal, I mean that they do not involve any translation in space, okay? And the others, the W plus and minus Ij, these are related, these are transition rates that involve spatial translation along the filament, so in space. Okay. Okay. So how should they look like, or how we hope well, we write them imposing local detail balance. That I don't know how many people already talked about. Maybe Francesco was discussing it. No one was discussing it. Well, at the level of Juan was discussing it, or Francesco one, no one else probably. Okay. Thierry. True. It's already a long week. You don't even remember what you did, what you did yesterday. Okay, so everything here is in a isothermal environment. So beta is the inverse temperature times the Boltzmann constant that can appear and disappear. Okay, there will be some free energies associated to being in the state Ij. Remember, these states are the conformational state of my motor on a single point along the filament. And there can be that once you do this transition between these two states, it can be that there is some reaction that is involved. So this reaction where there will be some chemical species alpha with a chemical potential alpha that can be involved in this transition. So this guy is essentially a sort of stoichiometric matrix. Just the point that I have to convert, I have to keep track of these internal states. So this kind of reaction is written in terms of the internal state of the molecules. So this guy is going to be plus or minus 1. Let's say, let's keep the stoichiometry simple. In the case, a chemical species, the chemical species alpha is binds or is released in the conformational change between I and J. Okay, and nothing else because we are standing still. So it's just a conformational change where you don't advance along the track. And then there are the other rates, the one that are related to motion. Okay. I notice that here I have to put a plus minus just because the states are the same because of the periodicity. So I cannot just, I have to distinguish also with the plus minus the two rates, just if you worry, because if you ask why there's no plus minus there. So in that case, there's gonna be some sort of free energy difference between these two states. There can be also intervention of reaction, but the point is that we are saying that this motor is working along against an external force that we consider for simplicity constant. So there's the same force whenever you displace. Okay, and there is a D is the typical is the periodicity of the filament, which is going to be the order of few nanometers, which is the displacement. Okay. And that's a model. The model tells you that there's gonna be a mean velocity of the particle, of the motor. Why I said particle? Because actually what you can do, and you can do in experiment, is you can isolate these motors. You can couple this motor, for example, to like a colloidal particle that you track and you trap, for example, with an optical tweezer. And essentially what you monitor, you cannot monitor in general the motor, you monitor this trapped particle. And so you can, with that, you can also look at the force thanks to the optical tweezer that you exert on the particle, and then if there's an elastic coupling to the motor. Okay, so the mean velocity is given by what? Well, I just have to take the rates that are related to jumping in space. So W plus ij minus W minus j I times multiply them by the probability. Sorry, this is ij. And I sum over all state I and j, right? And then I multiply by d because there's a dimension of length. Okay, so this is the typical this is the mean time scale of the transition space. With the probability to be in a certain state, I average, and with d, I just give the length of my jump. Okay. Here, assuming that everything else in my system but the degrees of freedom that I'm describing is at thermodynamic equilibrium, there will be an entropy production rate that is gonna be given by the usual formula. I sum over all states and I average the fluxes times the log ratio of transition rates. This is everything assuming that I am in a steady state. And okay. Yes. Yeah, I'm not sure. I think there's a JI here, right? Yeah. Sorry? Yeah, okay, yeah, because this is with the J, so if I do that and I rename that because I'm summing over all of them, then it's fine like that, okay? Right? Because it's a sum over all of them. Okay, thanks for... okay. So this is the general, this would be the general expression of how much free energy has been dissipated per unit temperature. And how much time do I have? 10 minutes? Okay. So if I now specialize it to, maybe I jump a little bit, I have it in the notes just to be specialized to the fact that this reaction is ATP hydrolysis. Okay. So, so essentially this means in Francesco's language is that there is just one one non-conservative force that's acting here. So there's only a delta mu, which is the one of ITP hydrolysis that enters at the end of the day in this expression. Well, you can write, if you explicit or if you put the local detail balance in, you well, you first have that you can write using also the stationary condition that expression. Okay. So this is whatever that comes from the conformational part that involves chemistry, and then the parts with translation in along the filament results in minus F times V naught. You can, this is just putting in the local detail balance expression there and averaging. And also, given the fact that I'm assuming that there's just non-conservative force coming from this only delta mu different, this mu delta mu, which is the ATP hydrolysis, I get that this guy here is going to boil down to delta mu times a chemical current, mean chemical current, where you see essentially that the chemical, the rate, the effective rate is given by the sum of these rates here, okay? So this is going to be more complex if I had more non-conservative forces acting here with more delta mu and j's. And I'm not saying that there's just one cycle in the system, okay? There can be at this moment, you can, because of how you design the problem, you can be more, this current J can be a composition of more than ones, okay? So this is the chemical work. It's the chemical work. Let me call it W chemical work. And this is the mechanical work on system. Okay, so in just a couple of minutes, what can I do here now? Well, So this is kind of, is very similar to what Francesco has written, for example, for chemical reaction network. It's just that now we have a piece that we have interpreted, we have put in the model in the form of a mechanical work, right? There's a part, there's a transition that is not in a chemical space, but is in the physical spaces due to translation. And so there will be, what this motor is doing free energy transduction. So it's using the power that comes from here to exert forces and then power on the external load. So what you can do, just to finish this part, what we can do is that we can actually imagine that we can interpret this now as a thermodynamic machine, right? So we can look at this is the power, the chemical power here is the power, is the work rate that we are inputting in the system, and the mechanical work is what we would like to read as the output power, right? So we are saying that T dot is equal to W dot in plus W dot out. This is by the very definition what we wrote at the beginning is positive, but we have that the W in is the delta mu J, and this W out is minus F V naught. And so we can define a thermodynamic efficiency, okay, of this object as the ratio between minus W dot out divided W dot in, right? So it's gonna be F V naught divided by delta mu J. Okay. Then, in particular, if this motor is designed in such a way that there is only one cycle current, so this means that, I mean, if this is a tight couple, there is a tight coupling between chemical events and jumps along the filament and translation. Well, in that case, we will have that this velocity, the mean velocity of our motor, is gonna be proportional to the chemical current, right? Proportionality factor being just the size of the jump that we make. So this means that for the efficiency, when we look at the tightly coupled system, we can rewrite the V naught, for example, as in terms of J and D. And so we have F D divided by delta mu, which is independent of the kinetics, right? So in this tightly coupled system, and someone said it already, I think, who said it during this two, I don't know, maybe it's I don't think it's the first time it's mentioned, right? That in the case of the tightly coupled system, there is the kinetics is not entering in this relation, okay? Because the chemical current here is dropping out everywhere. Okay. What do you mean? So this is every time. This means that every time that I do this, I mean, there was this filament, and it means that every time there is the translation in space, I'm also having this ATP going into ADP phosphate. So the tight coupling means that every time I'm displacing, this is concomitant with the chemical events of the ATP hydrolysis, okay? And this means that that's essentially, that's it. So whenever I look at the current in space, I can directly infer the current in chemical space. And so there's nothing more to know about that. Yeah, sure. You mean the fact that it is tight coupled enters in the choice that I made in the rate. This means that the ATP is only entering in the rates that are exactly. Okay. Okay, then in particular, maybe I can, let me see. Yeah, maybe I can just stop at that point, and tomorrow I just comment a little bit on that stuff, and then we go to what I anticipate about the coarse graining energetic through scales. Okay, that's it.